So Saif, if I go back, what I should do is that I should put the minus A here and put plus A here, right? Then everything is fine.
Yeah, I think so.
Yeah. Then A is positive. Yeah. Okay. All right. So the average position or the mean position of the wave function of the wave packet, say at time t0, is minus A, right? And the average momentum P0 is equal to H bar K0, okay? This is, you can think of it as the definition of K0, right? If I go back to my wave function, oh, it was K0 here. So this is the P0, okay? Right. So what this means is that after a time, say t, which is m times A by P0, right? So this is basically just the distance divided by the velocity. The wave packet we try to avoid using the term velocity in quantum mechanics, because velocity implies measuring the position of a particle with arbitrary accuracy in two subsequent, time, moments in time. And in quantum mechanics, that is a problematic, procedure. And that's why, we try to avoid talking about velocity. Instead, we try to express everything in terms of momentum. So but here, the velocity, we can associate the time as the time that the wave packet with the group velocity given by P0 by M hits the boundary. Okay, so after a time MA by P naught, the wave packet will hit the potential barrier. So then what we are interested in is that we are interested in these two quantities. After a long time, we are interested in what is the probability that the particle will get reflected. And that'll be given by the mod squared of the reflected part of the wave function as t goes to plus infinity. And R is known as the reflection coefficient. So this is the reflection coefficient. And then we are also interested in the probability that the particle will actually, will be transmitted, okay? So this is called the transmission coefficient. And because these are the only two possibilities possible, t plus r is equal to 1. And therefore, if I find one, I can find the other. So these are our aims. Physically, this is what we are going to be observing, because suppose that the way we do things is that suppose that we have a potential barrier and we prepare, say, 100 particles in the same initial state psi I, and then we essentially let them go, and then we observe how many of these particles make it through and how many are reflected back, and the ratios of those things and the fraction of those things should be roughly equal to the reflection coefficient and the transmission coefficient. Okay. All right. So how are we going to calculate this? So this is our strategy. So strategy will be, so we express the initial wave packet as a linear combination of exact energy eigenstate or momentum eigenstate. Okay, energy eigenstates. So once we have done that, we can evolve each eigenstate by simply multiplying it by e to the power minus I by h bar, that energy times t. Okay, and then we can just integrate over that. Okay, so this is going to be our strategy, but the concrete steps that we will do is the following. First, solve for the energy eigenfunctions psi e of x. Number two, express the initial state in terms of psi e's, and then we evolve and we get psi of x of t. So from psi of x of t, as t goes to plus infinity, we read off psi r and psi t and use them to compute r and t. Okay, pretty straightforward. What we're doing here at least should roughly make sense to you by now. Does it make sense, or should I stop and see why we are doing this? Okay, so in some previous lectures, several times I emphasized the fact that if you can find the energy eigenstate of a system, the dynamics is pretty easy. All you need to do is just multiply the energy eigenstate with this factor. Okay. With this factor. And if you have a general state, which is a linear combination of this energy eigenstate, then that state is automatically, evolved, because by linearity, that state is going to be a linear combination of the time evolved energy eigenstates. Okay, so the linear combination and the time evolution, they commute. Okay. All right, so any questions or comments or just confusions or something like that? Okay, let's do this, then I think it'll become clearer. So let's do step by step. What was step number 1? Solve for the energy eigenfunctions. Okay. So step number 1. Okay, which is okay. So there are 2 types of these things, right? So in region 1, the solution to the wave function, to the Schrodinger wave equation, time-independent wave equation, is going to be a e to the power I k1x plus b e to the power minus I k1x, where k1 is going to be 2me by h squared square root. Because in region 1, there is no potential, right? And in region 2, the solution is going to be just similar but different coefficient. Okay, where K2 is going to be 2m, the kinetic energy, divided by h squared square root. Okay. But you see that, if we multiply, psi in region 2, by, say, e to the power minus I by h bar e some positive energy times t, then we see that the second factor represents a wave moving to the left. Okay, and we don't expect that to happen, right? Because if I go back, our initial boundary condition is that, the wave function is going to come from the left, and it's going to bounce, and it's going to go away, and there'll be something that goes through. So we don't expect a wave function in this region to go in the left direction, right? Whereas in this region, we expect a wave function going either both to the right and to the left. So in region 2, we just expect the wave function to be going to the right. And therefore, and you can also show this, but we don't have to, is therefore what you do is that we just set this d to be 0, right? So therefore, we set d is equal to 0. Okay. So now, we have like part of the wave function in region 1, part of the wave function in region 2. Now what we have to do is that we have to join them into one wave function, right? And the way we do this is by imposing the boundary condition. And the boundary conditions are, is that, psi in region 1 must be equal to psi in region 2, and the derivative of psi in region 1 must be equal to the psi in region 2 derivative. So, sorry, this is the region 1 and region 2. Don't confuse that with the initial wave function, which is also psi I. Okay, so let's put quotations around this.